A probability that you would report should be a number between 0 and 1. Is it going to turn? So probability is a number that's between 0 and 1. You can change that into a percentage and make it go from 0 to 100%, but 100% is just the same as 1, right? So you cannot have a probability value that's larger than 1. And some people will be tempted to write down an answer that looks like it's larger than 1. So you guys are doing a test and ask you what's a probability of something, and then you punch some stuff in your calculator and you see that in your calculator you get 6.25 something. 6.25 is not a valid number for a probability. Like in your calculator, if you type in, type in 3 divided by, I don't know, something like 2,430,006. What do you get? So 3 divided by 2,400,000, I don't know, 90,006. So you'd be tempted to put 1.2 for 1.208 or whatever, right? So putting 1.2 will not be the correct answer. This is not a probability, right? And so this calculator has this e to the negative 6 there. You know what that means? Move the decimal point 6 to the left. And so that'll give you a number that's really, really, really small. That's close to 0. Okay? So this value that you would get is a probability, but the probability is actually 0.000012, which is a number between 0 and 1. And not 1.2, which is a number bigger than 1. So be careful how you write that. And we'll come up with some examples on how to deal with this stuff, probably in the next class. Yeah, in the book they look for, when they ask for probability, they usually ask for 3 decimal places. I like to see probability expressed with 4 decimal places. And if it's 0, 0, 0 with like 5 zeros, then some people just put 0, which isn't really quite correct. So let's say for our example, we got the probability of something happening to be, what was it, 3 divided by 2 million or something? So if you put this for your answer with 1.2046 e to the negative 6, then I know that that is a really small number. You could also put 5 zeros, 12046, which is also a small number. And sometimes they put 0.000, or sometimes they put 0 with a plus on top, which means it's a really, really small number, very close to 0. But what I don't want you to put is just 0. Yeah. Right. So saying something is 0 means that event will never happen. And this 3 out of 2.4 million is a really, really small probability, but it still might happen. So this would be the probability if I were to get 3 lotto tickets. This is a probability that I'll win the jackpot. It's really, really small, but it's not impossible. Give me an example of an impossible event. Winning the lottery, it's only impossible if you don't play. A man having a baby. Never happened, right? Never will. I don't think so. So that's an impossible event. A probability of 1 is an event that is certainly certain to happen. Give me an example of an event that's certain to happen. Your birthday will be on the same day every year. That's going to happen, definitely. Okay? All right. So somebody today said an impossible event is you walking outside and seeing a celebrity. Is that impossible?
Not probable.
Not probable, but it's not impossible. So it'll be one of these things where the likelihood is really, really small, but you never know. There might be somebody out there hanging out. Some startup guy. Those are celebrities. All right. Now, in terms of looking at the numbers, right down the middle, a 5 or 50% chance, or 0.5 or a 1/2 probability would be like your 50-50 chance. That's like tossing a coin and getting a heads or a tail. And anything above that, between 0.5 and 1, would be something that's likely to happen, and anything below that would be something that's not likely to happen. So basically, that's how you would look at probability. So I think later on we're going to be focusing on probabilities that's unlikely to happen, and we're going to put boundaries for when we would think that something is not likely or likely to happen. And I think a lot of times we have this idea that 0.05 is a special number that we're going to use as a boundary for something that's not likely to happen. But we'll talk about that later. But, this is just a quick chart. I think we got some general ideas of what probabilities are. So hearing something is an 85% chance of happening means it's a good thing, right? And hearing something that's like a 20% chance of happening is not so good. So I think we got this idea that over 50% is likely and under 50% is not likely. All right, complement. A complement of an event is denoted with a bar. Sometimes they denote it with a with a C for a power, and C stands for complement. So sometimes they write a complement to mean the same thing. So for an event A to happen, a complement would be for any other event other than A to happen. I didn't talk about dice. I thought I was going to talk about dice and I forgot. Well, there's a discussion about rolling dice in the book, so you can take a look at that. Round off rule. So there was a question earlier about how to round off probabilities. When expressing values of probabilities, you either give the exact fraction or decimal, or round off to 3 significant digits. So I personally like 4 significant digits, but if you put 3 significant digits, that's fine because that's what the book is stressing, and that's probably some of the answers that you have in your assignment.
It goes both ways. It just depends on how the question was worded.
Yeah.
If they had full decimal or they had some decimal.
Okay.
That's
I think the more decimals, the safer you are. So I would go for more decimal places. So here they mention probabilities of things that are not simple fractions, like 2/3 or 5/9. Usually, for some, if it's like a 1/2 or 1/4 or something that's easy enough, or 1/10, that's easy enough to understand, and you can leave it as a fraction. But if it's more complicated like this, it might be good to change it into a decimal. You can even change it into a percent, and so this is where you would just take the decimal and move the decimal point a couple of places to the right or something. Just make sure that if you write it as a percent, that you put the percent symbol down. So this is their general round-off rules. I don't know if I specify the round-off in the test, so I'm just going to leave it up to you to round it off to 4 decimal places, if you need to. Or you can just keep it as a fraction. Odds. We usually see the idea of odds in gambling, but it's also discussed in other things as well. So odds against an event A occurring is going to be a ratio. And here they say it's a probability of an event A happening divided by the probability of an event A not happening. That's kind of complicated. And usually expressed in the form A to B. So let's see what all this stuff means. Let's find a scenario that's a little bit more complicated than tossing a coin, like rolling one die. Let's roll one die. So your die is a 6-sided die. What's the probability of rolling a 5? 1 out of 6. So the probability of rolling a 5 is 1 out of 6. So what's the probability? I'll do this in another color. What's the probability of rolling something else aside from a 5? So I put 5 with a bar on top here. That'll be 5 out of 6. So if we're playing a game, I say I have one die here. If I roll a 5, then you win. If I roll anything else, then I win. Okay? So what are the odds against you? Well, 5 out of 6. So here's how we're going to do the odds against you. So our probability, let's say odds against rolling a 5. According to this, the odds is going to be a ratio, which we can start off writing as a fraction, and then we'll write it as an odds with a colon. So first we say the probability that we roll a 5, that's 1 out of 6, right? So that's P of A, or P of 5 in this case, 1 out of 6, divided by P of 5 bar, P of A bar, 5 out of 6. So this is a ratio. It's complicated. It's fractions, fraction divided by a fraction. But you could rewrite this, can't you? So I have a fraction divided by a fraction. It's the same thing as multiplying by the reciprocal business, right? And if I do that, I'll get a simpler fraction. So 1/6 times the reciprocal of 5/6 is 6/5. And then it looks like the 6's will cancel. And then I got 1/5. So you can write this fraction as a ratio 1:5. So if we play that game where I roll a die, if we get a 5, then you win. If you get any other number aside from the 5, then I win. So what are the odds against you? The odds against you are 1 in 5, or 1-5. The actual, yeah, so the odds in favor will just switch number 5-1. So in our example, the odds in favor will just be 5-1. Now, rolling that dice game or playing that dice game is fun, but it would be funner if we involved money in it, right? So let's say you pay me $1 to play, I roll the die, and then if you roll a 5, then I give you $1. And if I roll anything else other than a 5, then I take your money. Is that a fair game? Doesn't sound fair, huh? So, do you see my game? I roll the die. First, before I roll it, you give me money. You don't give me money. You put money down. You make a bet. You put $1 down. I roll the die, and if it comes up 5, then I give you $1 on top of your $1. But if you don't get a 5, then I take your $1. Okay, so that doesn't sound too fair, does it? What if we play the game where you put $1 down, I roll the die, if it lands on a 5, then I'm going to give you $10. If it lands on anything else, then I'm going to take your $1. Does that sound like a fair game? Sounds a little bit better, huh? So, the payoff odds against an event, this is usually how they do things in casinos. When they say the odds are 2-1, or the odds are 1-1, payoff odds, that first scenario that I gave you, where if you win, then I give you $1 for each $1 bet, that's a 1-1 odds, payoff odds, right? So if you play roulette and you bet on, there's a way to bet on a black or a red, depending on what the number is, then the payoff odds for those are 1-1. That means if you put down 5 chips, and if you win, you're going to get 5 chips. It's a 1-1 ratio. Now, the other game that we talked about is that if you put a $1 bet, then you win, then I give you $10 back, then those payoff odds are 10-1. And you guys seem to like that game a little bit better than the first one. So it turns out that these games are not fair. This is not fair to you as somebody who's playing, and this is not fair to me as somebody who's paying off. So what would be the fairest payoff for this? No. What? 5 to 1. The fairest payoff is that if you look at the actual probability and then use that for your payoff. And that's as fair as it gets. So 5 to 1. If your payoff odds are the same as your odds in favor of, then you have a fair game. So if these two odds are the same, if the payoff odds are the same as the odds in favor of, then you have a fair game. I want you to think about, I'm not going to talk about it much today, but if you have time, researching things, or if you happen to go to Vegas between now and Thursday, look at the roulette table. There are payoff odds for the roulette table, and you can actually compute the probability against you in a roulette table. So those odds, the actual odds in favor and the payoff odds are a little bit different. The difference seems really minor that when you play, it doesn't look like it makes a difference. But what happens in the long run for a casino is that the payoff odds go in their favor, that when millions and millions of people play roulette in this one casino, they're eventually going to be raking in a lot of money based on these odds.
Which one's the one where it spins?
Yeah, where it spins, you bet on the number. The thing is,
Right?
what?
And the color?
You can bet on color also. The thing is that the odds, the payoff odds that they computed were based on the roulette wheel having 1 through 36, having 36 numbers. But if you've ever seen a roulette table, there's a 0 and a double 0 that make it really out of 38. And so being 1 out of 38 versus 1 out of 36 is a really small difference, but that difference, like I said, in the long run, law of large numbers, in the long run, it's going to make the casino money.
So basically, right, when you see more of the possible.
Yes. Yes. All right. So this is the introduction to probability, and so now let's take a look at one of the big rules that we're going to talk about, what we're going to discuss, and that's the addition rule. So let's start by defining what we call a compound event. So compound event is an event that has 2 or more simple events. And here we introduce the word or. So we're going to use or and those two conjunctions are going to be important for us to tell the difference between them. And then they're going to be associated with a mathematical operation. So or, A or B. So in the trial, the probability of A or B is going to be the probability that we get A as an event, or the probability that we get B as an event, or, and this could happen, the probability that both of these things happen at the same time. So it depends on what the scenario is, and depends on what the event is for these things to happen. Let's take a look at rolling dice again, just as an example. Let's just roll one die. Let's take a look at an event that we roll an odd number. 1/2. So the event that we roll an odd number is going to be a combination of 3 events. Probability that we roll a 1, or a 3, or a 5. I think those are the only odd numbers between 1 and 6. So this would be an example of when you would use an OR statement. You would figure out what the probability of rolling a 3 is and rolling a 1 or a 3 or a 5. Okay? All right, now that wasn't a very exciting example, but let's take a look at some more ideas behind this OR business. So the idea behind this probability of finding an OR statement is that when we count the simple events that are involved here, we're basically going to count the number of simple events divided by the total. When we count the number of simple events, we want to make sure that we don't count a particular event more than once. And so that's what happens with this business about the compound event, is that when we're counting these things, we don't want to count it more than once. And so when we kind of set up a formula for this, our formula might automatically count some simple events more than once, and so we're just going to try to remember to subtract them out. So that's the basis for what's called the addition rule. Let's see if it comes up next. Here's an addition rule. A probability that A or B occurs is going to be, well, we're going to count the number of ways that A occurs and find the probability of that. We're going to count the number that B occurs and find the probability of that. Now, in finding the probability that A occurs and the probability that B occurs, there might be an overlap where A and B were both counted. And so here, we try to subtract out what we might have counted twice. So if we happen to have counted a couple of things twice, then we want to make sure we subtract that out. Sometimes we might not be able, this thing might not be an issue. Sometimes this thing might just be 0. There's no overlap between them. So in that case, then we can be sure that we're not counting that twice. So the next slide is Venn diagrams. Have you guys heard of Venn diagrams? Venn diagrams is a good way to try to visualize what's happening. So we count the probability of an event A happening, probability of an event B happening, and there might be this little area where we counted something twice, and so we want to subtract that out. So it turns out that if they have things in common, then subtracting out this probability is going to be important for us. Now, on the other hand, if you have two events that don't have anything in common, then this idea of P of A and B happening at the same time is going to be equal to 0 because there's no intersect between those two things. And if that's the case, then we have what's called disjoint events. Those two events do not overlap, so they're disjoint. And if you're certain that your events are disjoint, then you know the addition rule is not going to take into account that little subtraction business. So really, the addition rule has two formulas. One formula is that if they're not disjoint, then you need to subtract something out. Second formula, if they are disjoint, then you don't need to subtract anything out. Here they mentioned the complementary event business again. I don't think that's that big of a deal. So I'll skip over it real quick. And then some basic rules for the complement. The probability of A happening and the probability of a complement happening has to equal 100%, because those are if you're going to narrow it down to two events, those are the only two events. So something rolling a 5 or rolling something else that's not a 5. So that if you were to add those two probabilities up, you would get 100%, because that's everything in our sample space. So I think out of this, the most important formula probably would be the second one, to help us find probabilities of complements of things. So they don't come up with an example of the addition rule, but I wanted to dig one up, and I actually want to dig one up from the homework. So let's see if I can easily do that. Whoops, I got logged out. So I think I would find this type of problem in homework 4.3. Oh, by the way, if you didn't do the orientation, it's not going to allow you to do the homework. The orientation is just a simple set of, I don't know, there's like 8 or 10 problems there. And it's really easy. It'll take you about 5 minutes to go through. So if you're having problems getting in, then just make sure you do the orientation. So the kind of addition rule problem I think that I might have would involve a table. None of these are tables. Let's see if we can make a table out of this. Oops, that doesn't look good. Can you guys see? So here they talk about a pollster contacts 95 people in the 18 through 21 age brackets and find that 64 of them responded and 31 refused to respond. So something like this might get a little complicated when we start looking at just the numbers, so it might be good to put this in a table. So what we could do is we can create a table here with age brackets. And the age brackets that they talk about here is 18 through 21, 22 to 29. Is there more? That's it. And for each of these age brackets, they talk about people who respond or refuse to respond. So, by splitting this up like this, I think it might help us clear things up in terms of finding probabilities. And so we would fill in a table, let's say, for this age bracket, 64 of them respond and 31 refuse. So 64 and 31 for the refused. And in the next bracket, 220 respond and 44. This is 220. And 44 refuse to respond. So they also give us information about the total. So we can add this ourselves. This would be 595. But they actually gave us that number also. So out of the 18 to 21 bracket, there's 21 people that were surveyed. Or 95, sorry. 95 people that were surveyed. And this is how they split up. So 264 for that one. Actually, I should have done that in a different color. So we have our table given, or we would make it up. And then one of the things that might be good for us to try to figure out is the row and column total for each. So that might be useful. And it might be useful for us to figure out the the row totals as well. So this would be 284, 75. And here what we could do is we could just add either just the rows or just the columns, not both. We don't want to add them both. So that's going to double things. So I'm just going to add this 9. Is that right? 359? So just add, and if you can double check, if you can add these things, it should also be equal to 359. Pardon me? Oh, yeah, right here. Okay, good. All right, so let's try to answer their question here. Their question is, what's the probability that, find the probability of getting a person in the 22 to 29 age bracket or someone who responded. So, according to our formula, this is going to equal to the probability that we get somebody in the 22 to 29 age bracket plus the probability that somebody who responded minus the probability that we got somebody in the 22 to 29 age bracket and responded. So the probability that we select somebody in the age bracket would be, out of the total 359, there's 264 of them. 264 of them in the age bracket. Out of all the people that you collected, there are 284 of them that responded. Now the thing about this number, 284, because this is the number of people that responded. So the first number, the 264, came from adding up these two numbers. The 284 came from adding 64 and 220. But guess what? We counted 220 twice, right? We counted it when we looked for the age brackets, and we counted it when we looked for the people that responded. So we need to subtract out the 220 that we counted twice. So that's the addition rule. That make sense? Nope.
I see how you've got the 220 on the chart, but how would you put it into the formula? B minus B minus B and
So this is the people that responded and the people that are in this age bracket. So people that responded and people in the age bracket would be this cell that they have in common. And so that's how you would have gotten that from this thing. No, not and in addition. In fact, the word and should not be synonymous to addition. The word or would be synonymous to addition. And let's figure out what this numerator is. Our denominator is the same, which is good news, so I don't have to find common denominators. Let's just find the numerator. So can you guys punch this in your calculator and tell me what you get? Say it again. 328. Right? And since this is like a complicated fraction, you probably want to just punch it in and get a decimal or percentage. 0.9136. So 91%, that's a pretty high percentage, or that's a pretty high probability. Now let me do this a different way with the hopes of not confusing you, with the hopes of making things a little bit clearer. You're looking for the person in the 22 to 29 age bracket or the person who responded. So if I look at, let me see if I highlight this. Highlight. If I look at these values and I just go around adding these numbers, this probability, I could also have found this by saying 64 over 359 plus 220 over 359 plus 44 over 359. Then what should I get out of this? If you were to add the numerators together, the same thing. So you could have gotten the same answer without having to use the addition rule if you're given a table like this. So the thing about the addition rule is that the addition rule would be more useful if you weren't given a table, if you're given a bunch of probabilities instead of the actual raw number values. Okay. So this is just another way to find the same answer. Okay? So if you didn't quite understand the table way of doing this, then you could probably try to do it this way, where you just look at the body of the table and not bother looking at all the totals. Except the last grand total, you'll need the big total for everything. What? Frank is very helpful. Did he talk about this? Did you go? Yeah? Okay. So you might have some different insight that would be clear. How many people have seen Frank? Really, just one? You guys should go see him. It's in the plan. Okay. Where are we? So that's the addition rule. The next is the multiplication rule. The multiplication rule is a little bit different in the sense that we're looking for a probability that an event A has happened, and then after that's already happened, we're looking for the probability that another event will happen, or is about to happen. And they use the word "and" again, which is hopefully not to confuse the other "and" that we had earlier, where some things happening simultaneously. But in math, they try to associate words with certain symbols, like is the same thing as an equal sign. So it turns out that when you hear the word "or," we think of addition. When you think of the word "and," when you see the word "and," you think of multiplication. So the word "and" will, for us, be referring to a multiplication, some sort of multiplication. So, and this, again, this word "and" here refers to relating two events that are happening one after the other. So here, A and B means a probability that an event A occurs in the first trial, and then you run the same trial again, you get the probability that event B is happening on the second trial. So for this, I like the example of using a deck of cards. Are you guys comfortable with a deck of cards? So a deck of cards, how many in a deck of cards? So a deck of cards has 52. So we could start off with that. And we'll see if we can come up. Oh, let's talk about an event. Let's say A equals, out of the deck of cards you draw a card, and A's the, let's say you draw an ace. By that you mean you pick a card, and then the card that you get is an ace. And then let's say a heart is when you pick a card and you draw a heart. So we can define, or we can find a probability that we pick a card and we get an ace first, and then pick another card and we get a heart. Now this needs a little bit more information, because there's two scenarios at this point. If I'm doing this experiment twice, there's two things that can happen. One, I pick a card and then I take that card out and leave it out, and then I pick another card. And so those are my two cards. The other scenario is I pick a card, and then I put it back in, shuffle it, and pick another card. So that scenario is called with replacement, because you're replacing it. And in the first scenario is called without replacement. So you'll have two different answers for those two different probabilities. So with replacement and without replacement. We'll have two different answers. So maybe we'll try to find the answer to this in a few slides from now, when we define with and without replacement. So one way to try to structure something like this is with a tree diagram. And this particular slide has an example where you have a quiz with two problems. The first problem is a true-false problem, and the second problem is a multiple choice, A and B. So the question is, if you have this quiz and then you just randomly guess at the answers, what's the probability that you would get it correct? And for that, we need to figure out how many possible choices we have. And so part of the multiplication, this is more towards the section that we're going to skip, the counting, because this is really counting the number of you would have in your sample space, would involve some multiplication where the first question has 2 choices, the second question has 5 choices, and so the total number in your sample space would be 10 choices, so it would be 2 times 5. But so this kind of gives us your list of combinations of things. So maybe we should go back to this problem and finish it, because I'm not seeing the with replacement and without replacement. So let's go back to this problem and see if we can finish it. What's the probability of drawing an ace? So in a deck of cards, there's 4 aces out of 52 cards. So it'll be 4 out of 52. So let's say we took an ace out. What's the probability, and did we replace it? Let's say we replaced it. What's the probability that we get a heart after we take an ace out and then we replace it? What's the probability that we get a heart? How many hearts are there in a deck of cards? So there's 13 hearts in a deck of cards out of 52. So if we're doing this with replacement, when we go to pick our hearts, we still have a deck of 52, right? So the probability that we select an ace and a heart with replacement should equal to 4 out of 52 times 13 out of 52. Okay? And we can punch this in the calculator and get some number. But I'll just leave it like this. All right? So the idea that we do something without replacement means we have to assume that A has already occurred. And so that's the next slide that I kind of passed over, and I'm going to go back to. So this idea that we have here is called a conditional probability. Probability for a second event B should take into account the fact that the first event has already occurred. And so if we decide not to replace that card, we have to assume that we've taken out an ace. Okay? So let's take a look at the notation here. A conditional probability is written like this. This is a probability that B is going to occur given that A had already occurred. So let's B given A. Let's actually say this in more extended way. This is a probability that B will occur given that A had already occurred, already happened. So we have to take that into consideration. Okay? So whenever you're running an experiment twice, then we're looking at the second experiment occurring, provided that the first experiment had already occurred. The first event had already happened. They squeeze in a definition here of an independent event, or two events are independent. Two events are independent if one event happening does not change the probability for the second event happening. That's all they're saying here. So I'll just skip over this, and you guys can get this from the notes. But this is the actual multiplication rule that we're trying to eventually get to. So the multiplication rule is this. So the probability that A and B are happening is equal to the probability that A happens times the probability that B will happen given that A had already occurred. So let's go back to the example of drawing a card or drawing two cards. So if I draw a card and then I put the card back and then I draw the second card, then I can say that those two experiments are independent of each other, because after I draw out a card and I put it back and I reshuffle it, you're back to the original set. And so we found that in that case, a probability of drawing an ace times the probability of drawing a heart is, what was it again? It was 4 out of 52 times 13 out of 52. And we see that the probability of drawing a heart didn't change because of the first event happening. Now, if I take a look at the same scenario, except I don't put the other card back, then my probability should look a little bit different. I'll get the probability that I draw an ace for the first experiment times, and I'll get the probability that I draw a heart given that I already had drawn an ace. How's that different? Well, the probability that you draw an ace is still going to be 4 out of 52, because that's, you start off with the whole deck. Now if you take an ace out, you'll have one less card, right? So the probability that you would draw a heart, provided that you took an ace out, is going to be 13 out of one less card, 51. Pardon me? Oh, you could have drawn the ace of hearts, huh? Yeah, it would be 12 out of 51. Maybe this is a more complicated example. The more complicated examples. So we didn't give any requirements for the ace that we drew, right? So it is more complicated. Well, let me stick with 13 for now and say the ace that we drew wasn't a heart. In any case, you see that the probabilities were different from the first scenario when we had a replacement. Versus this scenario where we didn't have a replacement. So then your total probability here is 4 out of 52 times 13 out of 51. So the numbers will be very close to each other, but they'll still be a little bit different. So it does make a difference whether we do things with replacement or without replacement. All right. So this is something that will be a little bit more important later on. At this point, it's not really that big of a deal. So this is talking about the sample size as compared to the whole population. So if you have a really large population and your sample size is really small, then picking out of those things would be just the same as pretending that it's being replaced. You know, so I think what I wanted to get at was the whole idea about the independent versus not independent. You can think about the independent as something with replacement. Because if you replace it, you're kind of starting new, and then the second experiment will be just like the same as the first experiment. If you have something without replacement, then when you take something out, then your sample size changes. So this would be dependent. And what happens is that if you have a really big population and you're taking a small amount, you're taking one person out of that big population, and then you're looking at a second person in that big population, then it really doesn't matter, so you can treat it as if you're doing things with replacement. So that's this slide that they're talking about. If you have a really large population and you're talking about a really small sample, then you can probably treat it as something that's independent. Again, it won't be a big deal for us until we start talking about sampling sizes and stuff. Okay, I think this is where I want to, I kind of didn't want to worry about this part, but there's this phrase that we're going to be looking at a lot called at least one. And so I think it's I was going to skip over this section, but I'm going to just talk about this one concept. So, the probability of at least one. At least one is equivalent to saying one or more happening. So if we're talking about one or more happening, then the idea of a complement of that is nothing happening. Does that make sense? So, I'm trying to find a good example here. Huh. I can't think of a good example. Okay.
It's about, to run clock.
No.
And then what is the probability of being awakened by at least 1 o'clock?
So,
You figure out.
both
So the probability that the clock works is 0.85.
will fail.
The probability
Probability that at least one will work. So the probability of one alarm clock working, of the alarm clock, let's just say work. It's 0.85, so the probability that it will not work will be 0.15. Okay? So it sounds like this is the question that we want. We want to see what the probability that at least one of the alarm clocks will work. So this is at least one business. So finding the probability of one alarm clock working is 0.85, and then probability of another alarm clock working is 0.85 also. But what might be more interesting to find out is the probability that both of them will fail, right? And so if we count that, then the complement of that will say that at least one of them will work. Okay, let me say that again. So the probability that at least one will work would be the probability that one alarm clock would work, or the other alarm clock would work, or both of them will work. So that sounds like three things that we'd have to find. If we find out the probability that both of them will fail, that's something that we can find out, I think, rather quickly, and then we just take the complement of that. Then I know if both of them will fail, then that means neither of them work. So the opposite of both of them failing will be at least one of them working. Does that make sense? Okay, so let's find this probability that both of them will fail. So that would just be the probability that one of them won't work times the probability that the other one won't work, right? So probability that I put work with a bar on top, say it's not going to work, times the probability. And assuming these clocks are independent of each other, they're not connected, so we can just use the regular multiplication rule. 0.15 times 0.15. Which is equal to what? 0.0225. So that's a probability that both of them will fail, 0.0225. So the probability that at least one will work this probability will be equal to the complement of both failing. So 1 minus 0.0225, which is equal to what? 9775. So if you have two alarm clock and each alarm clock has an 85% chance of working, then you have a 0.9775 chance of being woken up by one or both of those alarm clocks. So that's a good probability. Okay? There's another cool example with birthdays. I just can't remember it off the top of my head, and kind of don't want to dive into it and get lost in the mix if I can't figure it out. So I think I won't even try. How many people are in this class right now? About 20? 19, 20. Turns out that if you have a room of like 35 people, then there's over 85% chance that two people have the same birthday. But if it's 19 or 20, I think it might be under 75% chance. So usually with a fairly large class, like a class of 35 or 40, I would make a bet with somebody that two people have the same birthday, because I know that there's an 85% chance, and so I'd win. But I think the way to figure out those probabilities is to actually use this at least one business. All right, so I'll skip over the rest of this, and hopefully you guys can read over some stuff because it's almost time anyways. So we'll say that we're done with Chapter 4. At least I'm done lecturing with Chapter 4. The rest of that stuff you can just try to research in the textbook. Your homework for Chapter 4 is due on Wednesday, and then on Thursday I'm going to lecture on Chapter 5 and probably get a little bit of Chapter 6. I don't know how far I'm going to get into Chapter 6. But we also need to spend a little bit of time reviewing. So what I'm going to try to do is that I'm going to try to make a recording for Chapter 6, and then I'll post that on the website for you guys to view, and that would be your lecture, since I probably won't get through all of Chapter 6 before the test.
And we'll get a review sheet next time?
And I'll put up the review sheet tonight online, so you can decide to download that. I'll probably take a quick look at that in class, but I won't go over it in detail, because I'm also going to provide a solution and some video solutions for it. Quiz 1 and Journal 1 is due tonight, and then the Journal 2 will be due on Friday. Quiz 2 will be due on Friday as well. All right?
So quiz number 1 is due today, right?
Yeah, so try to get it done tonight. If you do it by tomorrow, I probably won't. I'll probably download it tomorrow, so it won't be a big deal. But try to get it done. All right, see you guys on Thursday.